As you mentioned, this is a collaborative paper between Delia and myself, and I would like to start with thanking her for her contributions. And it's a collaboration I hope we can extend and expand in the future because, as was now said several times, I really found this theme terribly exciting and got carried away, and the presentation will probably be a bit too long, so I hope you will tolerate this. So what I want to go through is first give you some quantitative information about Asia's growing food demand and how Asia's livestock sector has responded. Now, this has already been discussed in some, or to some extent. I just want to put some figures on there. And the next part will be looking at infectious and parasitic disease dynamics, looking at some of the impacts of these diseases, and finally, some elements of a response. So here to start with, this is global human population over the past 4,000 years. And you could see that we are at a time, let's say 50 years from 1850, when human population reached about 1 billion, to 2050, when it is projected to reach 9.3 billion. That is the century of unprecedented human population growth. It has never grown that much, either in relative or absolute terms, and I predict it will never grow that much in absolute and relative terms later on. So we are living in this century in which actually mankind has become the strongest evolutionary force on this planet. And the projections of food demand, even if you take high bounds, low bounds, is that over the next 50 years, as much food will have to be produced as in the past 10,000 years. Now, this perhaps gives an indication of the challenge humankind is facing. Now, looking at Asia, already now, with much lower per capita incomes than the industrialized world, Asia's food density expenditure is equal to or bigger to that in industrialized countries. And we have been talking about income growth. So this is purchasing power income growth in the two biggest Asian economies, India and China, since 1990, so that is 20 years ago. And in China, it has grown more than fivefold over 20 years. And in India, which is not really known to be the most dynamic economy, it has grown by nearly threefold. I have to say, I would have been very happy if my income had grown threefold over the past 20 years. It hasn't done so. And if we then look at how people allocate their income, still a lot in the developing world of the additional dollar goes to food, mainly better food, so that out of one additional dollar earned, about 35, 40 cents go to food items, and it is mainly high value or higher value food items, as was mentioned, vegetables, fruit, and meat products, and fish. So these are now just some projections of poultry meat demand growth, and you see the black spots are India, China, Asia. This here is egg. So eggs are projected to be demanded far more in India, the Indian subcontinent. If we did pigs, it would be more East Asia. Milk throughout the world, dairy demand. So the growth is huge. And most of the additional production will take place where the additional demand happens. Although more production will be traded, still the bulk of growth occurs where the bulk of demand growth is. So how have livestock sectors adapted or changed? So the first thing is total number of livestock has grown tremendously. Not all species have grown by the same margin, so poultry has grown particularly fast across all regions. Now, small ruminants have grown particularly fast in South Asia and pigs in East Asia. Then we come to the intensification process, so a much faster turnover of animals through better animal health, of course, but mainly through feeding high-density rations, that is more grain feeding, genetic selection, and these high-performing animals are shipped all across the globe. Larger farming units, concentration of these units in certain production areas, either close to feed resources or close to markets. Then an increased use of feed additives, so those can be hormones, they can be acidifiers, and one class is antibiotics as growth promotants. The sector has stratified, that is specialization. You have breeders, you have multipliers, you have the final finishers, and with that, different forms of contract farming, and we have longer cross-border supply chains. So these are, let's say, the reactions or the responses of the livestock sector. And this has led, just an example here. In East Asia, chicken meat has trebled over the past 20 years, while the number of chicken has doubled. So this is an indication of the intensification process. In Southeast Asia, chicken meat output has grown by 400%, chicken numbers by 300. So intensification has not been quite as strong and rapid, but growth has still been very high. And if we take South Asia, numbers have grown almost in line with meat production. So intensification, although occurring, is not or has not occurred yet. And let's say similar processes occur with pigs. And if we take in East Asia, China, what is true is that growth is slowing down, but I think we are still far away from a post-growth society or post-growth economy. So even if, let's say, growth in pig numbers in China is only 3% now, that still means an additional 1.5 million pigs. So it is still growing. And one characteristic of livestock sectors here is the coexistence of various systems. So you find extremely modern pig production units or chicken production units with processing units and retail, just as you have in industrialized countries, sometimes even more advanced. You have the very low-tech so-called backyard systems and live bird markets and processing, and a lot of intermediate stages that maybe purchase day-old chicks from the integrated producers, but they fatten them. Or vice versa, you have large-scale integrated producers that sell their birds in live bird markets. So this system coexistence is another, let's say, risk factor, I would say, if we talk about diseases and disease emergence. So what are the ecological consequences of this livestock sector growth? So first is land use changes. Yes, land being converted into, let's say, non-agricultural land into agricultural land. And that usually leads to habitat fragmentation. So you have different patches of land with different vegetation. And habitat fragmentation leads to larger interfaces between wildlife populations and livestock populations or human populations. So you have more chances of crossover, and it also changes ecological balances so that some hosts may have to look for a different host than they previously had. Another point is the expansion of irrigated areas. Since more feed has to be produced, more land, and also more food, of course, more land is irrigated. And irrigated areas provide habitats for waterborne parasites, so for example Leptospira, but also a lot for insect vectors which breed in those waters. So you have an expansion of vectors of diseases. Thirdly, we have created these large, housed, rapid turnover, genetically homogeneous farmed animals, exposed to heavy use of antimicrobials, And this has created what I would call an ecosystem in its own right. We have here a new ecosystem which exerts its own selective pressures that are different from those that occur in, let's say, the wild. For example, in housed animals, they're not, or pathogens are not exposed to sunlight anymore, so you don't have the UV light which kills. They have a constant temperature most of the time. It's very humid, so it is a very particular ecosystem. And the constant exposure to antimicrobials exerts another selective pressure. And then finally, we have these complex value chains, which again provide novel pathways of transmission and contact. And if we look at pathogen reservoirs, or let's say reservoirs of microbes, one can sort of distinguish three major pools. One is wildlife, and wildlife is not only, let's say, the spectacular large wildlife, it is very much rodents, small animals, birds, so those we don't necessarily see all the time. The domestic animal pool and the human pool. And these diseases, one always says they don't respect national borders, but they don't even necessarily respect species borders. So they can move from one species to the other. And for example, we as humans, we harbor more microbial cells than we have body cells. And the same applies to other animals or animal species. And what happens from the wildlife pool, they may go into the domestic pool. Domestic animals may be dead-end hosts, but domestic animals may be amplifying hosts, exposing humans. Humans can get infected. What can happen is that the pathogen develops the capacity to move from human to human transmission. So the dynamics can be summarized or categorized into three major events. One is territorial expansion. So you move an animal, let's say even a breeding animal, from North America to China. It brings with it North American pathogens, and they invade East Asia. The second one is changes in virulence within the system, because let's say management changes, and jumping from one species to the other. Now, this is not a novel or new process. Here, having reviewed all sorts of emerging zoonotic disease events since 1940, the map has already been shown by Jimmy. What I would like to highlight is that the red dots, which are sort of, or let's say the blue ones, which are the new dots, and the red ones, which are sort of the older emergence events. The older emergence events were very frequently in North America and Europe, where agriculture intensified in the second half of the last century, while the blue ones seem to be more equally distributed across the world. And I would hypothesize that emergence is moving more towards the areas that are intensifying. And some recent events are, of course, SARS and Nipah. And just to show that this is a process that has been ongoing for a long time, this is the genetic makeup of the 209H1N1. And if you look carefully, the original swine H1N1 gene here, the green gene segment, actually transferred from humans into pigs in 1918. And pigs have been propagating this gene. And then there is another event which occurred from, here it's the gray one, in 68. The PB gene came through wild ducks or waterfowl to humans into pigs. There is one which moved into pigs in 1998. And then there has been this translocation from a Eurasian swine gene into this novel H1N1 virus in 1979. So this is a process that goes on all the time, and fortunately, most of the time it doesn't lead to anything, but sometimes it does lead to a pathogen that jumps to humans and then is transmissible between humans. Now, a virus that exemplifies all three characteristics, species jump, virulence shift, and territorial expansion, is H5N1, the Chinese, or let's say the strain that originated in China, which from wild waterfowl moved to domestic poultry, has infected humans and cats. The virulence shift, most influenza virus from waterfowl are actually low path, and they have transformed into high path, and this has happened in Italy, it has happened in Holland, it has happened in Canada, it has happened in Chile, and it has happened in China and in Mexico. So it is not a unique event for H5N1. You have high path H7N1, H7N3, and so on and so forth. And territorial expansion, H5N1 has moved to more than 60 countries on 3 continents. This shows the importance of trade and, of course, also wild birds. And if we just look at selection for virulence, this is a review done by Alison Galvani on factors that increase virulence selection. You can see that, and the ones I'm particularly concerned about is host homogeneity. The more homogeneous a host population is, the more it selects for pathogen virulence. Host cluster connectivity, that is, how easily does a virus get, or a pathogen, from one cluster of hosts to another cluster of hosts. So you have the contract farming, which get their day-old chicks or their bird from some central unit, and it moves to the different contract farmers. Within host strain competition, so the LPAIs are different variants. There are at least 16 H's and 9 N's or so, which compete within the host. And then vaccination, depending on the type of vaccine, can increase virulence or decrease, and culling will always increase or select for increased virulence because one culls the resistant hosts, and treatment can have both effects. So we see that the large-scale mass production actually favors selection for virulent pathogens, even under the highest biosecurity concerns. Now coming to antimicrobials. If you put these large numbers of animals in a dense, confined environment, they tend to get chronic, low-grade infections. And looking at antimicrobial use, this is data on the left in the pie chart from the US, but from other countries where it is available, one can see the same distribution, namely of total antimicrobials, maybe 10% are used in humans, and the remaining 90% are used in animals. And 82% are actually used in farm animals. And if you know a bit about farm animals, you know that apart from a dairy cow or a high-value breeding animal, you don't use antimicrobials very much for therapy. It is used for prophylactic reasons, and in many places also as growth promotant. And on the right you see the amount of antimicrobial use per ton of meat. US is by far for the countries for which data exists, with about 4.4 kg per ton. You can see at the bottom the Nordic countries where growth and prophylactic use has been banned, going down to less than 0.5 or 0.1. Now just taking these numbers and multiplying it by, let's say, meat production in East and Southeast Asia, taking the low value, you get to some 5,000 tons of antibiotic use in Asian countries, for which there is at least no data in the public domain. But we do have evidence of antimicrobial resistance from the region, and here you can see that almost half of Salmonella isolates are resistant to antibiotics, to tetracyclines. And the same or similar values you get for other enteric bacteria, also from South Asia, maybe not quite as much. And these bacteria, they pass on the gift. As we heard yesterday that farmers pass on the gift, these bacteria pass on the antibiotic resistance genes to other bacteria. And from these bacteria, some of them are in the soil, some aren't, they go to human bacteria. So it is transmitted from animals to humans, and from humans it may be transmitted back to animals, and so on. So what are the impacts of zoonotic diseases? The first one, is income forgone through reduced economic activity. That is when all of a sudden there is a scare and people stay put. The second is cost of precautionary and preventive measures, so all the quarantines and scanning at airports and so on. Cost of control activities, so vaccinations, culling, etc. And then finally, reduced productivity and welfare both in animals and humans. So this is a slide I borrowed from Subhash, SARS. If you remember, SARS in 2002 or so, a scare went around the world and economic activity dropped very sharply, and it drops in countries where you don't even have a SARS case. It is simply the fear of a disease which causes this great economic loss. And these are some estimates of costs of, let's say, new zoonoses. So Nipah in Malaysia in 98, 99, which actually only, still more than you would want, caused 106 deaths, had an estimated cost of $0.7 billion. The SARS epidemic, with less than 1,000 casualties, has been estimated to have cost $40 billion. H5N1 in Asia, 20 billion. And now H1N1 caused a lot more human death than H5N1, an estimated almost 300,000. Now H1N1, in a way we were lucky, it was a high path virus for humans, but of low transmissibility. H1N1 was a lower path virus, but of high transmissibility. Right now the H3N2 variant is low path and low transmissibility. So maybe the next one is going to be high path and high transmissibility. Now coming to zoonoses which are so-called endemic established. And there human medics have come up with what they call a DALY, a disability adjusted life year, which is the sum of years of life lost and disability years, so that they can weight or put a weight to diseases that affect younger people, older people, have high mortalities or high sequential or consequential costs. So by far the highest disease burden is through diarrheas. Now of course they don't give the cause of diarrheas, but if we assume that between 1/3 and 10% are from pathogens that come from animals, we still are on top, or they still remain on top of the list of human disease burden. We have tuberculosis, then you see in South Asia, Leishmania and Japanese encephalitis, two diseases we don't hear very much about, are causing relatively high burdens. While if we look at East Asia and Southeast Asia, we find foodborne trematodes that come with seafood, so crustacean and fish, and echinococcosis in East Asia. And then again, rabies is pretty high in South Asia, not so much in East Asia, where it still is important. So although emergence is not necessarily related to smallholder, small-scale production, the burden of disease probably is, as one can see here by the overlay of small livestock keeper or smallholder poor livestock keepers and disease events, or disease burden, sorry. What is the cost of antimicrobial resistance? Again there, it's hard to find anything in the literature on Asia, but so in the US, where it has been studied, longer hospitalization, about 11 days, increased treatment because you need to use more expensive drugs of $20,000, higher case fatality rate, double. And in that US study, the increased cost was about $10,000 per hospitalized case. So that is an average of non-resistant and resistant. So if 1 in 10,000 US citizens is hospitalized in a year, this would amount to $250 million, $250 million. And then a third, let's say a fourth cost element is that in areas where resistance might be common, just the general prescription moves towards more expensive drugs. So we just want to come up with some possible public health priorities. One would definitely be to reduce the incidence of foodborne diseases and parasitic infections in East and Southeast Asia. And we need to, I would say, reduce the risk of these novel emerging diseases because the cost to the economy is so disproportionately high. And even though the evidence is not there yet, I would say we need to promote prudent use of antimicrobials in farm animals. So coming to the response elements, one, let's say, element would be to move away from the silo approach to health management to holistic multidisciplinary approach to agriculture, health research and risk management. So this is horizontal cooperation and coordination between disciplines. So it is human health, it is animal health, but it is also ecology, it is evolutionary modeling and so on. The second one is a more preventive approach, that is to address the causes of these burdens rather than always react to the emergencies. And then finally, or thirdly, because we will never be able to prevent or to have zero risk, we need much better supranational early warning, disease reporting, and disease control systems. So that is what I would call vertical coordination and cooperation. So with this, I thank you. I've probably overstretched my time, but maybe there is some sun behind the clouds. I don't know. So thank you.